Hi everybody, in this video I am going to be talking about function transformations using horizontal shifts of graphs of functions. To understand what this means, let's take a look at our first example here, which says given y equal to f of x, draw y equal to f of x plus 2. So here you see the graph of a function y equal to f of x, and this actually looks like the square root function. And using this graph, we have to draw the graph of y equal to f of x plus 2. So, we have to transform the graph of f of x to f of x plus 2, and it is very important to observe here that in this function, in this transformed function f of x plus 2, the 2 that you are adding is to the argument inside the function. So, you are adding a 2 to x and then you are applying the function f on x plus 2, whereas in vertical shifting of graphs, we saw that the function was something like f of x plus 2. So, the 2 is outside the function, the thing that you are adding or subtracting is outside the function, but in this case you are essentially adding the 2 to the argument. So, this is a very different situation from this situation over here. So, once again, the best way to think about this and understand this situation is to think of functions as machines. So, let us imagine our original function f of x as a machine f, and let us say that for some input x naught, the output is y naught. Now, this input output pair x naught comma y naught, what will this correspond to on the new graph? That is what I really want you to think about. And the answer is that in this case, to get the same input y naught, you have to actually modify your input for the new function. So, your new function is f of x plus 2. So, this new machine, what it is really doing is it is taking some input, adding a 2 to that and then applying the function f. So, this means that to get the same output y naught, what you will have to do is to modify your input in some way. And what do you really have to do? You simply have to modify your input to x naught minus 2, because if this input goes into this machine, first a 2 is added to this, so you get x naught, and then f is applied on top, and therefore you will get the output y naught. So, what is going to happen here is the original input output pair x naught comma y naught will transform to the new input output pair x naught minus 2 comma y naught. What this means in terms of the graph is, let us take this point over here and let us call it x naught comma y naught on the original graph. Now, on the new graph, this point will actually transform to x naught minus 2 comma y naught. So, the new point will have an x coordinate 2 units lower than this coordinate x naught. So, which means that the new point will lie 2 units to the left of the original point. So, this point will actually transform to this point over here, and actually the same thing is going to happen to every point on the graph. Every point on the graph will see a transformation of its x coordinate by a subtraction of 2 units, and what that will mean is that your overall graph will shift horizontally 2 units to the left. So, let us see what that looks like. I have plotted it here for you. So, here is the original graph, the white line y equal to f of x, the white curve, and the dotted green curve is y equal to f of x plus 2. So, every point on the original graph has moved 2 units to the left. So, for example, if you see this point here, this has moved 2 units to the left. If you see this point here, it has moved 2 units to the left. This point here is also moved 2 units to the left, and therefore, that is what is really happened here. There has been a horizontal shift 2 units towards the left because the argument x was increased to or changed to x plus 2. So, by adding 2, you shifted the graph 2 units to the left. Now, what if instead of adding something to the argument, you subtract something from the argument? So, now we have to take y equal to f of x and transform it into f of x minus 3. And once again, it is important to observe that this expression here or this function here is actually different from f of x and then you subtract a 3 from f of x. So, this is very different. You are subtracting 3 from the function, but here you are subtracting 3 from the argument. So, So, once again, if you think of functions as machines and you think of the original function f, which takes some input and produces some output, x naught produces y naught, then the new machine f of x minus 3, it's easy to see that this new machine, what it's doing is it's subtracting a 3 from the argument and then applying the function f. So, to get the same output y naught, you have to change your input argument to x naught plus 3. So, the original input output pair x naught y naught is transforming to the new input output pair x naught plus 3 y naught. And what that means graphically is that every point on the graph, let us take this point over here and let us call this x naught y naught on the original graph. This will move 3 units to the right and give me this new point x naught plus 3 comma y naught on the new graph, and the same translation rightward is going to happen for every point on the graph. So, the entire graph will shift horizontally rightward by 3 units, and here is what that looks like. This is my graph of y equal to f of x, this one, and this dotted curve here is the graph of y equal to f of x minus 3, and you can see that every point has shifted 3 units to the right. So, if you see this point here, you see this has gone over here, and then this point over here, you can see this has gone over here. So, there has been a 3 units right shift in a horizontal manner of the original graph. So, that is what we mean by horizontal shifting. Let us summarize what we saw. So, if you are transforming y equal to f of x to y equal to f of x plus c, what that really does is it sends every point x naught comma y naught on the original graph to the corresponding point x naught minus c comma y naught on the new graph, and therefore, this means that the entire graph will shift horizontally leftward by c units, and that will give us the new graph f of x plus c. And you can think of this as an advance of the original graph. So, the original graph is advancing by c units towards the left. Why advancing? Because the same output y naught, which was originally coming for the input x naught, is now coming earlier at x naught minus c. So, you can think of this whole thing as an advancing of the entire graph c units towards the left. And similarly, if you have to transform y equal to f of x to y equal to f of x minus c, then what this transformation does is it sends any point x naught y naught on the original graph to this corresponding new point x naught plus c comma y naught on the new graph, and this means that the whole graph is shifting rightward by c units, and you can think of this shift as a delay of the original graph. And why a delay? Because the same output y naught, which was originally coming for the input x naught, is now coming for the input x naught plus c. So, the same output is now coming later, it is coming for a higher input, and that is why a delay. So, this is horizontal leftward or rightward shifting. Let me help you visualize this even more clearly through a simulation. So, here is a simulation of a function y equal to f of x, and I can actually plot in this simulation y equal to f of x plus c and y equal to f of x minus c, and I can change my values of c. So, let me first plot y equal to f of x plus c. Right now c is equal to 0. So, you just see the original graph in the simulation, but now let me increase the value of c, and as I increase the value of c, what should happen? I should see an advance. The original graph should shift c units towards the left, and the more I increase c, the more that leftward shift should be. So, let us see. So, if you can see the behavior now, and right now I have set c at 3.6. So, you can see that you can ignore this minus sign, you can just observe that the original graph has shifted 3.6 units towards the left, and instead if I plot f of x minus c and now increase the value of c, I should see a delay, and the delays should increase as I increase the value of c. So, let us do that, and now you can see that the graph is shifting rightward, and let me set c at 4.3. So, you can see that the original graph has shifted 4.3 units towards the right? So a delay of 4.3 units. Now let's quickly solve a couple of questions using this concept of horizontal shifting. The first one says the graph of y equal to x square is shown below, and we have to draw these four graphs: x plus 1 whole square, x square plus 1, x minus 1 whole square, and x square minus 1. Now very important to recognize the structure of these transformed functions. If your original function is y equal to f of x, then the first one is x plus 1 whole square. So you are essentially changing the argument x to x plus 1. So this one here is a case where you are changing the argument itself and you are actually calculating f of x plus 1. But this one here is x square plus 1. So you are first calculating x square and then adding 1. So this one is actually f of x and then you add a 1 outside. And similarly, this one here is x minus 1 whole square. So you are first changing the argument to x minus 1 and then squaring. So this is f of x minus 1. This is f of x minus 1 because the argument is changing, and this one here correspondingly is f of x first and then you subtract a 1 to get this. So this means that this one here is an advance, a horizontal advance, and this one here is a vertically upward shift, and this one should be a horizontal delay, f of x minus 1, and this one here should be a vertically downward shift. So I am just using abbreviations here. So let us quickly plot all of them one by one. So the first part is y equal to x plus 1 whole square. So this should be a advance of 1 unit. So this vertex will come over here, this point will come over here, this point will move over here, and then maybe this point will move over here. So I have something like this, I think should, yes, so this would be the graph of x plus 1 whole square. What about x square plus 1? So this is a vertically upward shift of 1 unit because you are adding 1 to x square. So the whole thing will shift vertically upward. So this point will move over here, this one moves over here, this one moves over here, and then you get something like this. So you get the idea. So x square plus 1. What about x minus 1 whole square? So this should be a delay of 1 unit. It's a horizontal rightward shift of 1 unit. So this point goes over here, this one moves over here, this one moves over here, and then maybe this point here I can plot it over here. So I'll get something like this, and that would be x minus 1 whole square, and then finally x square minus 1 would be a vertically downward shift of 1 unit. So this point moves over here, this one moves over here, this one moves over here, and then I'll get something like this. Yes, it's a crude drawing, but you get the idea. So 4 different kinds of shifts all in the same problem. Now let's see question 2. It says the graph of y equal to x square is shown below. Draw the graphs of first y equal to x minus 2 whole square minus 1, and then y equal to x plus 1 whole square plus half. So let's once again decode the structure of these expressions. So if your original function is y equal to f of x, so f is the square function, then first you are doing in this first part, you are first doing a delay of 2 units, a rightward shift of 2 units, and then a downward shift of 1 unit. So this is how you have to see this combination. First you think of this, just this function x minus 2 whole square. It's a rightward shift of the original function by 2 units, a delay by 2 units, and then you're subtracting 1. So a downward shift by 1 unit. And similarly over here, you first think of this x plus 1 whole square, which would be a leftward shift of 1 unit of the original function, and then you add half to it, so an upward shift of half units. So let's plot these two functions one by one. So let's say y equal to x minus 2 whole square minus 1. So first let me just plot this x minus 2 whole square. So that would be a rightward shift of 2 units, and let me just plot a few points to help me complete my graph. So this one moves over here, this point here moves over here, and this original point moves over here, and then this point over here moves over here. So I get something like this. Once again, it's a crude drawing, but you get the sense. And then I add, I subtract 1. So, this subtraction of 1 should lead to a vertically downward shift of 1 unit. So, let me just do that. So, this one point comes over here, this one comes over here, this point comes over here, and here you get this one over here. So, I think I should be able to plot this now. So, something like this. So, there are two motions or two translations that happened here. First, a horizontally rightward shift or a delay of 2 units because of this x minus 2 square, and then a downward shift of 1 unit because you had this minus 1 here. So, that is how you think of combinations of translations. Let us look at this next one, x plus half whole square plus x plus 1 whole square plus half. So, this first part here should correspond to a horizontal leftward shift of 1 unit. So, let us do that. It is an advance of 1 unit. So, this point here, this point over here, and this point over here, and then this point over here, and this point over here. So, I have about 5 points now to complete my plot. So, something like this. Okay, that should work, and then I am adding a half to it. So, I am now going to vertically translate this graph or shift this graph upward by half units. Okay, so let us do that. So, this point here comes over here, this one over here, and this one over here, and then this one over here, and maybe this one over here. So, I have now a few points to help me complete my plot. So, yeah, something like this. Okay, these are not really intersecting, so that is just the crudeness of my drawing. So, what is really happening here is first a leftward shift of half of 1 unit like this, and then an upward shift of half units like this. So, that is really the two translations that happened here. So, this is all about horizontal translations. I hope you are now clear about this concept. I hope you liked it. Let me know what you think in the comments.